There is a shape I want you to think about, not a complicated shape, the simplest possible shape, a cylinder with a flat top and roughly vertical sides. You have seen this shape thousands of times. You have walked past it in parks. You have sat on it. You have photographed your children standing on top of it. You know exactly what. It is when it is 3 feet wide and 2 feet tall in a forest clearing. You call it a stump. You do not hesitate. The shape speaks for itself, and your brain reads it in less than a second. Flat top, vertical sides, circular base. Something was here. Something was removed. What remains is the bottom of the thing that was removed, and the bottom is always flat because the removal happened at a horizontal plane. You know all of this without thinking about it. The knowledge is so obvious it does not feel like knowledge. It feels like seeing. Now I want to ask you something. What happens to that knowledge when the shape gets larger? Not a little larger, enormously larger. What happens when the flat top is not 3 feet across but 3 miles across? What happens when the vertical sides are not 2 feet high but 2,000 feet high? Does the shape change? No, the shape is identical. Every structural characteristic that told you stump when you were looking at something in a forest clearing is still present. The flat top is still flat. The sides are still vertical. The base is still roughly circular. The only thing that changed is the number, the scale, and I want to ask whether the scale is a good enough reason to stop reading the shape the way you read it when it was smaller, because I have been looking at mountains, at mesas, at buttes, at the flat-topped formations on every continent on this planet. And the shape they keep showing me is the same shape, and I cannot stop asking what that means. This is not a claim. I want to be precise about that from the very beginning of this video, because the subject attracts a kind of content that makes claims it cannot support, and I do not want to be part of that. What I am doing is something different. I am asking questions. I am pointing at shapes and asking why those shapes look the way they look, and whether the explanations we have been given fully account for what we are seeing. I am not going to tell you that mountains are tree stumps. I am going to ask you to look at the shapes with me and think about what it would take to produce them, and I am going to ask you to hold that thinking open for longer than we usually hold these things open, because I think the open position is the honest one here, and I think the honest position is more interesting than the closed one. Let's start with what a stump actually is, not metaphorically, structurally. When a large tree is cut, what remains is the base section of the trunk. The base section is the widest part of the tree, the point where the trunk meets the root system, the point where the wood is densest and most compressed. The top of what remains is flat, because the cut was made at a horizontal plane. The sides are roughly vertical because the trunk at that point is roughly cylindrical. The base is roughly circular because the cross-section of a trunk is roughly circular. Over time, as the stump ages and the wood weathers and begins to decay, the outer layers harden and the inner material softens. The exterior develops a harder crust. The top may become slightly concave as the softer inner wood compresses and sinks. The sides begin to show the texture of the wood grain, which runs vertically. In some species, the stump will send up new growth, shoots emerging from the outer ring, from the cambium layer, just beneath the bark, reaching upward toward a sky that the original tree no longer occupies. If you come back to that stump after 50 years, you may find a ring of new trees growing from the outer edge of the original base. A circle of younger growth surrounding a center that is now hollow or depressed, all of them standing where the edges of the original trunk once stood. Now I want to describe something else. There is a formation in northern Arizona called the San Francisco Peaks. There is a formation in New Mexico called Shiprock. There is a formation in Wyoming that the Lakota people called Bear Lodge and that we now call by a different name. There are formations in the American Southwest called mesas and buttes. There are formations in Venezuela called tepuis. There are formations in southern Africa called kopjes and in selbergs. There are formations in Australia called the ranges of the Kimberley and the sandstone plateaus of Arnhem Land. There are formations in Antarctica called nunataks, and across all of these, across every continent, across every geological period, across every material from sandstone to basalt to granite to quartzite, the shape recurs. Flat top, vertical or near vertical sides, roughly circular or polygonal base when viewed from above, isolated from the surrounding terrain, rising abruptly from flat plains or valley floors. Sometimes accompanied by a debris field at the base, material that has fallen away from the main structure over time, arranged in a way that suggests it shed from the central formation rather than accumulated from outside it. I keep asking myself what kind of prior structure, what prior object would leave those characteristics behind. Across that diversity of material and geography, and the answer that keeps presenting itself is the same answer I get when I look at a 3-foot stump in a forest clearing. Something was here. Something was removed. What remains is the base. Here is where I want to spend some time on the geology, because I think the geology is interesting, and I think understanding what the geological explanations actually say is important for understanding what they do and do not account for. The standard explanation for flat-topped mountains is differential erosion. The idea is this. A landscape contains rock of varying hardness. Over geological time, weathering and erosion wear away the softer rock more quickly than the harder rock. Where a cap of particularly hard rock sits on top of softer material, the hard cap protects the material beneath it from erosion. While everything around it is worn away, what remains after millions of years of this process is a raised formation, whose top is defined by the hard cap and whose sides are the eroded edges of the underlying material. The top is flat because the hard cap was deposited as a flat horizontal layer. The sides are steep because the boundary between the hard cap and the surrounding eroded material is sharp. This is real. This is how real geological processes work, and the formations I am describing are real formations that have real geological histories that geologists have studied in real detail. I am not dismissing any of that, but here is the question I keep returning to. Differential erosion explains how the flat top was preserved. It does not explain where the flat top came from. Something had to deposit a hard horizontal layer in order for that layer to later protect the material beneath it. What deposited the layer? How did it become flat? Why does the same basic structure, flat hard cap on softer material, recur with such consistency across such diverse geological contexts? The explanation explains the survival. It does not fully explain the origin, and it is the origin that I keep asking about. Consider how sedimentary rock forms. Sediment is deposited in layers horizontally by water or wind. Over time, the layers compact and harden into rock. The layering remains horizontal because that is how it was deposited. A flat horizontal layer of hard caprock could be a resistant sedimentary layer deposited at a certain point. In geological history, harder than what came after it, that is possible, that happens. But is this sufficient to explain every case? Consider the global distribution of flat-topped formations, the variety of materials they are made of, and their diverse geological contexts, some in sedimentary sequences, some in volcanic settings, some in ancient basement rock. Is a single mechanism doing all this work? Or is it applied selectively? Cases where it fits and those that don't are adjusted to comply. That is not science, that is the appearance of explanation. The difference between these two things is worth paying attention to. Let's discuss columnar jointing, a real geological phenomenon. When basalt cools and contracts after eruption or intrusion, fractures develop. These fractures run perpendicular to the cooling surface, forming columns. Typically with 4 to 7 sides, 6-sided columns are most common. The structure looks like vertical pillars packed tightly together, each a polygon in cross-section, running parallel from top to bottom. The Giant's Causeway in Northern Ireland is a famous example. Fingal's Cave in Scotland, the columns at Devil's Postpile in California. These are beautiful formations, and their geological explanation is well established. But here's what I find interesting. The same structural characteristic appears, vertical parallel columns of roughly uniform diameter, in many flat-topped formations. And when I look at a cross-section of a large tree trunk, I see something analogous. The wood fibers in a tree run vertically, parallel to each other. In very old, large trees, the wood near the center is compressed and dense, darker. This is what we call heartwood. The wood near the outside is less compressed, lighter, more recently formed, what we call sapwood. The overall cross-section shows concentric rings, each ring representing a year of growth, older, denser material toward the center. I am not saying that columnar basalt is petrified tree fiber. I am asking whether the structural similarity between columnar formations and large trees deserves more attention. The structural logic is similar, vertical parallel elements of roughly uniform cross-section, harder outer material, softer or more hollow interior, roughly circular overall cross-section. These are not random similarities. They are specific structural characteristics. What to make of that I genuinely do not know. But I do not think the right response to not knowing is to stop looking. Let me try to take the question somewhere more concrete. If you wanted to look for evidence that a very large biological structure had been mineralized, what would you look for? You would look for the preservation of organic structural patterns in rock. You would look for concentricity, for the kind of ring structure that biological growth produces. You would look for the preservation of what we call cellular geometry, the characteristic patterns that living tissue creates at a microscopic level. You would look for chemical signatures consistent with the original biological material, traces of carbon compounds, of silica that replaced cellulose, of mineral patterns that organic structures leave behind when they are replaced molecule by molecule. And here is what I keep asking. Has anyone looked for those things systematically? In the formations I am describing? Has anyone taken core samples from the interior of a large flat-topped mountain and analyzed the microstructure at a level of detail that would reveal biological origin if it were there? Has anyone done the chemistry? Has anyone done the imaging? The technology exists. The analytical tools exist. The question is whether anyone has applied them to this specific question, at this specific scale, with this specific hypothesis in mind. And from everything I have been able to find, the answer appears to be no, not because the technology is unavailable, not because the access is impossible, because the question has not been taken seriously enough to motivate the research. The formations sit in their national parks and tourist destinations, photographed millions of times, and the interior chemistry of their rock has not been analyzed for biological origin, because the question has not been asked, that absence of asking. That is the thing I cannot set aside. Now I want to address the scale question directly because I think it is where most people's thinking stops. And I want to try to move past the stopping point. The objection goes like this: trees do not grow 40 miles wide. Trees do not grow a mile tall. The scale I seem to be implying is so far outside the range of anything we know about living things that the hypothesis can be dismissed on that basis alone, without needing to examine the formations in detail. I understand that objection. I want to take it seriously, but I want to ask a few questions about it. The first question is, how do we know the upper limit of what biological organisms can be? The largest organism currently living on Earth by mass is a fungal network in Oregon, called the Armillaria osteae, which covers approximately 2,385 acres, or roughly 3.7 square miles. It is a single organism. It has been growing for an estimated 8,000 years. It is not a tree, but it is biological and it is enormous. The largest organisms ever confirmed to have existed were not the blue whale. They were the sauropod dinosaurs, some of which may have weighed over 100 tons, and before them the giant arthropods of the Carboniferous and the lycopsid trees of the same period, whose remains are the coal we burn today. The upper bound of biological scale is not a fixed number. It is a function of the conditions available at a given time: different atmosphere, different gravity, different available nutrients, different competitive pressures, different timescales of development, and the possible scale of living things shifts. I am not saying the conditions for 40-mile trees existed or exist. I am asking whether we can confidently rule it out based on what we know about this planet's history. And I do not think we can. Here is the atmospheric question that I find most difficult to set aside. During the Carboniferous period, atmospheric oxygen reached approximately 35% compared to the roughly 21% of today. That elevated oxygen supported insects the size of eagles, millipedes the length of a car. The metabolic extravagance of a world running on more air than we breathe now, what produced that oxygen? Oxygen is produced by photosynthesis. Every molecule of oxygen in the atmosphere came from a plant that captured sunlight and split water and released oxygen as a byproduct. A 35% oxygen atmosphere requires photosynthesis at a scale difficult to explain with typical organisms. The Standard Model invokes dense global forests of lycopsid trees, reaching 150 feet, packed across every continent. I am not going to tell you that model is wrong, but I will ask whether it is sufficient. Whether the arithmetic of photosynthetic output at 150 feet, even across global coverage, produces a 35% oxygen atmosphere, or whether the arithmetic requires assumptions generous enough that a different explanation might do the same work with less strain. I have sat with that arithmetic and I have found it uncomfortable. The discomfort is not proof of anything. But I think it is worth sitting with rather than resolving too quickly. Consider what happens when you look at the coal seams of the world. The coal in the ground, the compressed plant material that powered the Industrial Revolution, came from the Carboniferous forests. The compression ratio of organic material into coal is roughly 8 to 10 times by volume. A coal seam 1 foot thick represents 8 to 10 feet of original plant material. The major coal seams of Appalachia, of the Ruhr Valley, of the Donbas, of Siberia, measure hundreds of feet thick. Hundreds of feet of coal represent thousands of feet of original plant material, compressed over 300 million years. The forests that produced those coal seams were not small. The organisms in them were not modest. When I try to reconcile the scale of coal production with the official height estimates for carboniferous trees, the reconciliation requires assumptions about density of coverage that push against what the fossil record actually shows. The density required to produce that much coal from 150-foot trees is higher than what fossil root systems suggest. Something in the arithmetic does not close cleanly, and when an arithmetic does not close cleanly, the honest response is to ask which variable is wrong. I think the variable most likely wrong is the one we cannot directly measure, which is the height. And height is the one thing that a stump, whether 3 feet wide or 3 miles wide, does not preserve. The height is always the part that is missing. I want to spend some time on specific formations because the specific is more useful than the general when asking questions. There is a formation in New Mexico that rises 1,583 feet from the desert floor. It has a roughly circular base. Its sides are nearly vertical. At its base, 3 narrow ridges extend outward, radiating from the central structure, like lines drawn from a center point. The official explanation is that it is a volcanic plug, the hardened magma core of an ancient volcano, and that the 3 radiating ridges are dikes. Intrusions of magma that filled cracks in the surrounding rock during the original volcanic event and then hardened. That explanation is plausible. Magma does fill cracks. Dikes are real geological features. But here is the observation I cannot set aside. The 3 radiating ridges extend outward and slightly downward. Magma flowing from a central volcanic source through horizontal cracks would be expected to spread at roughly the same elevation. These ridges run downward. They extend from the base of the central structure toward the surrounding plain at an angle, more consistent with a root structure extending from a base toward the soil than with a magma intrusion. I am not saying that is what they are. I am asking whether anyone has asked that question seriously with the analytical tools that would be required to distinguish between the two possibilities, and I do not think anyone has. There is a formation in Venezuela that I find equally compelling as a question. It rises nearly 9,000 feet from the surrounding jungle. Its walls are vertical for most of that height. Its top is flat and covered with a unique ecosystem, species that evolved in isolation on the summit because the summit has been isolated for long enough. The rock that forms it dates to approximately 1.7 billion years ago. The official explanation is that it is a remnant of a sandstone formation that once covered vast areas of South America and has since eroded away everywhere. I am not going to dispute the age of the rock or the fact that the surrounding material has been eroded, but I want to ask about the walls. The walls are nearly vertical for thousands of feet. Conventional erosion processes, the movement of water and wind across rock surfaces, do not typically produce vertical walls. They produce slopes, they produce talus, they produce the gradual angle of repose that any material takes. Truly vertical walls of that height require that the material at the wall surface was removed catastrophically, all at once. Or that the material there was always absent, that what we are looking at is not a wall produced by erosion but an edge, the original edge of something whose lateral extent ended here, an edge of a structure rather than a wall carved by time. I find that possibility interesting. I think it deserves a question. I want to address the objection that living things cannot reach the scale I seem to be gesturing toward. I want to address it by pointing at time, not at any specific number of years, at the principle of time as a variable. The largest organisms that have ever existed were not the largest organisms that could have existed given more time, or given different conditions, or given the removal of competitive pressures that kept them from growing larger. They were the largest organisms that happened to exist given the specific conditions of the specific geological period. Change the conditions and the maximum size changes. We know this because we can observe it across geological time. The largest land animals that have ever existed were much larger than the largest land animals that exist now. The largest marine organisms that have ever existed were much larger than most of what lives in the ocean today. Scale is not fixed. Scale is a response to conditions, and the conditions of this planet have not been constant. They have varied enormously over geological time, in ways that we understand in broad outline and in ways that we may not yet understand at all. The question of what the maximum possible scale of a photosynthetic organism might have been under the most favorable conditions this planet has ever produced is a question I do not think anyone has seriously tried to answer. It requires assumptions about atmospheric composition, gravity, nutrient availability, and time. What I keep coming back to after all of this is the shape, the flat top, the vertical sides, the circular base, the debris at the bottom arranged as if it shed from the structure rather than accumulated against it. The way the center is sometimes hollow or depressed below the level of the outer ring, the occasional presence of something that looks like new growth emerging from the outer edge, younger formations rising from the rim of the original base. These are not arbitrary characteristics, they are specific, they are consistent, they appear across materials and geographies and geological periods. A single explanatory mechanism, differential erosion, is not fully accounting for, at least not in the sense of explaining the origin of the shape. The shape was there before the erosion began. The erosion preserved it, and the shape, if you are willing to look at it without explanation, is the shape of a base, the shape of what remains. When everything above a certain point has been removed, the shape that the bottom of something makes when the top is gone. I do not know what the top looked like. I do not know how tall it was. I do not know what removed it, whether it was cut or fell. I do not know whether the thing that produced these shapes was biological in the way that a tree is biological or something else I have no category for. I do not know whether the question can be answered. With the tools we currently have, what I know is that the shape keeps showing up. Every continent, every material, every geological period that left surface formations accessible to observation. The flat top and the vertical sides and the circular base keep appearing in the landscape, and the explanation attached does not fully answer the question of origin. It answers the question of survival, and survival, while important, is not the same as beginning. The question of beginning is still open. The question of what produced the shape that erosion then preserved is still open, and I think open questions at that scale deserve serious investigation. The shape is asking a question. The landscape is asking a question. And the honest answer to that question at this moment is, I do not know, but I think it is time to find out. There is one more thing I want to sit with before I close, and it is the thing that I think is the hardest to articulate. It is about what it would mean to be right, not for geology, not for science, but for the way we understand where we are and what we are standing inside of. Because if the flat-topped formations on this planet are the bases of organisms that once reached into the sky at a scale we currently cannot imagine, then the landscape we have inherited is not the landscape we think it is. The valleys we live in are not random accidents of erosion. They are the spaces between things that were once there and are no longer. The plains we farm are the floors of a world whose ceiling we have never seen. The horizon we look at in every direction contains, at various points, the bases of things that once extended far beyond any horizon we can currently perceive, and the sky above those bases, the sky that the tops of those things once occupied, is simply sky now empty, without any record of what it held. The sky does not remember, only the stone at the base remembers, and the stone is speaking, if we are willing to listen to it in the language it is using, which is the language of shape, the language of flat tops and vertical sides and circular bases and debris fields arranged like shed material, and hollow centers where the oldest, densest part of the original structure has compressed and sunk below the level of the outer ring. I think we are not very good at listening to that language at this scale. I think we have been trained to read the language of process rather than form. We ask how things formed and we build explanations around processes, around erosion and deposition and volcanism and tectonics, and those explanations are powerful and largely correct about the processes they describe. But I think there is another kind of reading that the landscape invites. A reading that starts with form and asks what the form itself is telling us before we attach a process to it. And when I do that reading, when I look at the shapes without the explanations already loaded, the shapes keep telling me the same thing. Something was here. It was very large. It reached very high. It ended. What remains is the base. And the base, despite everything that has happened to it in the time since the ending, is still showing the structure of what it was part of. Still flat on top, still vertical on the sides, still roughly circular at the base. Still, after all this time, the unmistakable shape of a bottom, the shape that anything makes when it has a top that is gone. I do not know how to close this in a way that resolves the question, because the question does not resolve. That is the honest answer. The question opens and it keeps opening, and the further you follow it, the more it opens and the more of the landscape it reaches out to encompass, until you are not looking at individual formations anymore, but at the entire surface of the planet and asking what it was before it was this. What did it look like from above when whatever was here was still here? What would a person standing on the surface of this planet have seen if they had been here before this? What would the horizon have looked like? How far up would you have had to look to see the sky? Those questions do not have answers I can give you. They may not have answers anyone can give, at least not with the tools currently available and the seriousness currently applied. But I think they are real questions. I think the flat tops are asking them every day, in every landscape on every continent, and I think the fact that we walk past them and take photographs of them and write geological descriptions of their caprock without asking the deepest question they are raising is one of the stranger facts about the moment in history we occupy.